I would like to invite now Mr. Imam from the Department of Civil and Environmental Engineering at the University of Surrey in the United Kingdom. He will talk about the bridge score reliability under changing environmental conditions.
Okay, good morning, ladies and gentlemen. A lot has been told yesterday about scour and how important it is in terms of the hazard that we need to consider on a lifetime basis on the assessment of bridge structures. So this is a study that looks at the bridge scour reliability of bridge piers under changing environmental conditions. So effectively looking at how potentially climate change manifested in changing environmental conditions might affect the reliability and therefore the risks of bridge structures. We all know bridge scour is the most common cause for bridge failure, so this is undoubtedly a big problem. There are still bridges nowadays failing through scour. And one of the biggest challenges is that most prediction methods are empirical, so most of the assessment models for scour have been developed for laboratory conditions, small-scale specimens, and there is an important scale effect. So people have shown that they might be inadequate in predicting accurately scour in real-life conditions, in real field conditions. Here I have itemized a number of sources of uncertainty. So considering bridge reliability under scour conditions, sources of uncertainties can be river and flow characteristics. Obviously the effect of the changing environmental conditions and in climate change, which in itself is uncertain. Unknown foundation depths. There are still a lot of bridges, old bridges, which we don't know how much the depth of the foundation is, so that poses again a big uncertainty in the whole problem. And as I mentioned, the use of empirical models. So what I'm trying to present here is a basic framework for how we can quantify scour reliability and how we can potentially take into account the effect of climate change on scour reliability. So a few examples of bridges that have failed due to scour in the past. And I will not pause a lot of time here. Bridge scour is obviously the erosion of the local area around the bridge piers, and some photographs about scour here. So the biggest problem of scour is local scour, which tends to concentrate around bridge piers and abutments. And this is effectively a figure which was taken by the IPCC report for climate change, which shows effectively how the change in climate might affect extreme events. Okay? So obviously, if this is our current climate, so this is a distribution of an extreme event. Okay? If the distribution changes rightwards through time, as you can see, we are expecting to have more record extreme flows. And obviously, when we are considering scour, we are looking at extreme flow events and how that might affect the stability of the structure. So what we used in this framework is the HEC method for local scour assessment, which you can see the equation there. It's a well-used international standard for scour assessment. So the parameters here that are important, there are 4 parameters that take into account different geometrical aspects of the bridge. So the shape of the pier, angle of the path of the water on the pier, stream bed conditions, which relate to whether you have clear water or light water conditions, and obviously the riverbed material size, which is an important geotechnical parameter for calculating the stability of the pier. The depth of the flow is directly affected by the flow itself. Okay, and then you have here the flow number, which is a hydraulic parameter, which is a function of the velocity. And then how we set up the probabilistic framework. You can see the limit state here. We were looking at the limit state of exceedance of the foundation depth at the local pier, so we didn't extend that into the system of the bridge itself, so we were looking at it from a component point of view. And we, having that limit state, then you can carry out a Monte Carlo analysis to calculate the annual probability of failure, and then aggregating the annual probabilities, you can have a cumulative probability of failure over the lifetime. In Monte Carlo, we calculated it was using 2 million samples. And these are the random variables which show what kind of uncertainties we have quantified, we have taken into account in the analysis. Okay, so things like geometrical parameters with small variations here, but also more important parameters, hydraulic parameters. One parameter that I want to pose on is this modeling uncertainty. So I come back to what I said earlier about the use of empirical models on scar assessments. So people have done comparisons of these models with real field measurements of scar, and they have shown that there are great differences in the scar depth predictions given by these theoretical models. So the mean value of these comparisons actually has shown a mean value of 0.55, okay? And also note the very big variability of these comparisons of field measurements with the theoretical models. Okay, so how we tackle the problem is effectively do a parametric study to see how climate change might affect the properties of the distribution of the annual flow, and we base our analysis on the maximum annual flow with a return period of 2 years. Okay? That flow is obtained from annual maxima series of the flood estimation handbook, which is a well-known software in the UK, which gives you effectively all the flow predictions for all the rivers in the UK. So doing a statistical analysis, the expected annual flow was shown to best describe or generalize the extreme value distribution. So what effectively that method does is it looks at all the historical data of floods and then it extrapolates that. One of the things we assumed obviously to carry out the analysis and simplify this, we assume that flow events in different years are assumed to be independent to each other. Okay? And as I said, the parametric study to quantify the changing conditions was manifested through changes in the distribution parameters. So if you imagine that this is a distribution of the maximum flow, okay, what we assume is how a change in the mean of that distribution, an increase in the mean or an increase in the standard deviation or variability of that distribution will affect the scar reliability of the bridge pier. And this is the framework, which effectively starts with obtaining the statistical properties, setting out the Monte Carlo analysis in MATLAB, okay, estimating through the random variables the annual probability of failure, then calculating, bringing together the annual probabilities, estimating the time-dependent cumulative probability, and then doing that for different scenarios of changes in the statistical properties of the distribution. So some results here. So this shows you the distribution of the maximum annual flow and how that changes with a change in its mean parameters. So here we have assumed that the increases are 20, 40, and 60%. One of the biggest challenges effectively determine how much will that change be. Okay? So in the UK, for example, there have been studies looking at how potentially climate change might affect extreme river flows. Okay? And there's a lot of dispute about what that number is. Some rivers are expected to be affected much more, some rivers are expected to be affected less than that. And this is an example of how a change in the standard deviation and the variability will affect the distribution. Okay, and then using that for the probabilistic analysis, you can get the time evolution of the probability of failure. Okay, so this is a scenario of assuming an increasing mean in the distribution of the maximum flow, and this is the case of capturing an increased variability, so an increase in the standard deviation of the assumed probability. And the analysis was carried out for a time horizon of 60 years, as you can see, for different increases. Okay, and both figures show both the annual probabilities, but also the cumulative probabilities of failure. Obviously, it's evident that in the first few years, there is a small influence on the probability of failure, but as you move forward into the future, you have it's more evident the change in the probability of failure. Okay, we haven't looked at the target probability. Obviously, this will depend from structure to structure. So it was out of the scope of our study to define the target probability and compare the probability of failure with that target. So these results are for a specific foundation depth of 4.5 meters, and we also did an analysis to see how the effect of the foundation depth might affect the probability of failure. So this shows you the influence of different foundation depths on the cumulative probability of failure. So these are the previous results, so for a foundation depth of 4.1, and you can see how much the influence is on changing even smaller foundation depth. So this is a significant parameter that greatly influences the probability of failure and requires attention more reliably defining what is the foundation depth. Obviously, one of the things that we haven't considered in this study, notice that in this specific study, if you have a foundation depth of 4 meters, you end up having very large probabilities of failure. So obviously, there is a correlation between the foundation depth and the river flow as well. So obviously, the more river flow you have, the deeper your foundation is expected to be, but we haven't taken that into account in our analysis. We just based our discharge, river discharge constant, and then we played with the foundation depths. And then this shows a summary of the effect of the scar modeling uncertainty, which, as I said, is very, very important. So the lower curves show you the cumulative probability, assuming no modeling uncertainty taken into account in the analysis. And here you can see what happens if you consider the modeling uncertainty into your analysis. So again, a big increase in the probability of failure. Okay, so usually in the order of 1 to 2 magnitudes. Okay. The other important observation through that is that when you start considering the modeling uncertainty here, you can see that then the effect of the changes in the variability of the flow itself are overshadowed by that big uncertainty in the modeling parameter, because you have a very big COV of 0.52, which was obtained from the comparisons of the field measurements of scar with the theoretical predictions. Okay, so this was a framework to show effectively how you can quantify the changing environmental conditions on scour reliability. Okay, so what the results show that initially you don't have many large influence on the probability of failure, but as you move forward into the time horizon, that changes in the probabilities of failure become more and more important. The foundation depth and the scour modeling uncertainty were found to have a significant influence on scour failure probability. Okay, so that shows the importance of determining accurately these two parameters, especially foundation depth, and considering all these bridges, which we don't have any records about what type of foundations they have and what is the depth of the foundations. And as I said, the case study that we have carried out, which was a case study on a real bridge, showed that the effects of the changing flow characteristics reduce with reducing foundation depth. So effectively, the lower the foundation depth you have in a bridge, the less the impact of the climate change is expected to be on that. And with that, I conclude my presentation. I'm happy to answer any questions.
Thank you very much for this interesting presentation. I have one question in regard to the uncertainty of the future development of the flow properties. So did you try to, so this is a kind of parameter uncertainty, right? So you don't know exactly how the mean value and the standard deviation of this extreme value distribution will develop. Have you tried to integrate this parameter uncertainty into the reliability analysis in order to get a predictive curve of the development of the probability of failure over time?
So what we did effectively is that the flood estimation handbook gives you the distribution of the extreme value of the flow. So it gives you a value, a mean value and the standard deviation of that extreme distribution. And what we did is we looked at how incremental changes in that mean and the standard deviation of the extreme value distribution will affect the probability of failure. So that will obviously mean that we need to convert that increase in the mean into the statistical parameters that describe that generalized extreme value distribution and put that into the analysis.
Yeah, that's kind of a parameter study, but you could also try to integrate the uncertainty of the future development of the mean.
Yes, so yeah, we didn't take into account that uncertainty. So that parameter was assumed to be deterministic in itself, but obviously you can put a distribution in the parameter itself or look at how that uncertainty will impact the scar reliability.
One more
study the sensitivity to this parameter because you can have to 90% or even larger than 100% this modeling uncertainty is covered. Because you don't know exactly where is the foundation, you don't know everything.
Yes, so we did, this was, probably you know better than me, this was an NCHRB report which actually collected all the field measurements carried out in the states and compared to, so we didn't look at how that coefficient of variation might affect the